Slope deviation method. The slope deflection method is a technique used in structural engineering to determine the deflections and slopes in a beam or structure subjected to loads. This method is based on dividing the structure into small segments and calculating the slopes and deflections at each point of the structure using the equations of equilibrium and the appropriate boundary conditions. The slope is calculated as the derivative of the deflection with respect to the position along the structure, and the deflections of adjacent segments are summed to obtain the total deflection at a given point in the structure. Principles. The fundamental principles behind the slope deflection method are based on understanding how loads applied to a structure generate deformations, and how we can quantify these deformations using this method. Deformation under load. When loads are applied to a structure, whether they are forces, moments, or load distributions, the structure tends to deform. These deformations can manifest themselves as displacements or rotations in different parts of the structure. Load deformation relationship. There is a direct relationship between the loads applied to a structure and the resulting deformations. The greater the load applied, the greater the deformation experienced by the structure. This relationship may be linear in some cases, as in the analysis of beams under uniform loads, but may be more complex in more complicated structures. Slope deflection method as an analysis tool. The slope deflection method allows us to quantify these deformations by dividing the structure into small segments and calculating the deflections and slopes at each point of the structure. By applying the equations of equilibrium and the appropriate boundary conditions, we can determine how these deflections and slopes vary along the structure. Interpretation of results. Once the deflections and slopes in the structure have been calculated, we can interpret these results to understand how the structure deforms under the applied loads. This is crucial to ensure that the structure is strong and safe enough for its intended use. In summary, the slope deflection method provides us with a tool to understand and quantify the deformations in a structure under applied loads, which is essential for the design and analysis of safe and efficient structures. This method is useful for several reasons. Its study is based on the stiffness method. It is easy to apply for some structures. There is a good interpretation of the deformations of structures when determining slopes and deflections. The method is based on calculating the bending moments of a structure in which the deformations are restrained and correcting the resulting imbalances by imposing linear rotations and displacements at the nodes of the structure. Degrees of freedom. When a structure is loaded, specific points of the structure, called nodes, will undergo displacements. These displacements are called degrees of freedom of the structure. In the displacement method, the degrees of freedom are important since the unknowns are known when the method is applied. History. The deflection slope method was originally developed by Heinrich Manderla and Otto Mohr in order to study secondary forces in reinforcement. Later, in 1915, G. A. Manny developed an improved version and applied it to the analysis of indeterminate beams and frames. Slope deflection method. To obtain the general form of the slope deflection equations, we will consider the typical span AB of a continuous beam as shown in the figure, which is subjected to any load and has constant EI. We want to relate the internal end moments MAB and MBA in the beam to its 3 degrees of freedom, that is, the angular displacements A and B, and the linear displacement increment that could be caused by relative settlement between the supports. The moments will be considered positive in the clockwise direction. The equations developed use the superposition principle and consider separately the effects caused by each of the angular displacements at A, B, and increment, and then by the loads. Angular displacement in A. We can determine the moment MAB required to cause this displacement using the conjugate beam method. Applying a summation of moments at B and A, we obtain the moments of the conjugate beam, MAB and MBA. Angular displacement in B. Same way as in node B, only now the embedded end is node A. Relative linear displacement increment. The moment is related to the displacement increment, using the conjugate beam method. In this case, VC is free at both points. By summing moments at B we obtain, as M is counterclockwise, slope deflection equations. If the end moments due to each displacement and the load end moments are added together, they can be written as Since these two equations are similar, the result can be expressed with a single equation. If we designate one span end as near end, N, and the other as far end, F, the stiffness of the span member is represented by K equals I/L. And if we designate the rotation of the span chord, psi equals increment/L, we can write for internal span, or end span with recessed far end. Slope equations deviation. Where internal moment at near span end, this moment is positive and clockwise acting on the span. Modulus of elasticity of material and span stiffness, K equals I/L. Slopes of the near and far ends or angular displacements of span at the supports. The angles are measured in radians and are positive if clockwise. Rotation of the span chord due to a linear displacement, i.e., psi equals increment/L. This angle is measured in radians and is positive if clockwise. Moment of embedment in the near support. The moment is positive if it is clockwise acting on the span. This equation is a load displacement relationship and is the general slope deflection equation. When used for problem solving, this equation is applied twice to each span of a member AB. That is, the application is from A to B and from B to A for span AB. Clear with articulated end. Sometimes an end span of a beam or frame is supported by a pin or roller at its far end, as in the following image. When this occurs, the moment on the pin or roller must be zero. If the angular displacement of B on this pin does not have to be determined, we can modify the general slope deflection equation so that it has to be applied only once to the span. To accomplish this, we apply EQ to each end of the beam. This gives the following two equations. Here the embedment moment at the near support is equal to 0, because at the far end it is hinged. In addition, the embedment moment can be obtained using the table in the right-hand column. Multiplying the first equation by 2 and subtracting the second equation, the unknown theta f is eliminated and results only for clear end with hinged or overrolled far end. Since the moment at the far end is 0, only one application of this equation is necessary for the end span. This simplifies the analysis since the general equation would require two applications for this span, and the unknown angular displacement theta b at the end support would be involved. Analysis procedure. Degrees of freedom. Name all supports and nodes to identify the spans of the beam or frame between the nodes. By drawing the bending shape of the structure, it will be possible to identify the number of degrees of freedom. Each node can in general have an angular displacement and a linear displacement. Compatibility at the nodes is preserved if the members that are rigidly connected to a node experience the same displacements as the node. If these displacements are unknown, and in general they will be, then for convenience assume that they act in the positive direction so that they generate a clockwise rotation of a member or node. Slope equations deviation. The slope deflection equations relate the unknown moments applied to the nodes to the displacements of the nodes for any span of the structure. If there is a load on the span, calculate the embedment moments using the tables. If a node has a linear displacement increment, calculate psi equals increment/L in adjacent spans. Apply EQ to each span end, thus generating two offset slope equations for each span. However, if the far end of a span at the end of a beam or frame is hinged, apply EQ. Constrained end only, thus generating only one deflection slope equation for the span. Equilibrium equations. Write an equilibrium equation for each unknown degree of freedom of the structure. Each of these equations must be expressed in terms of unknown internal moments, as specified by the deflection-dependent equations. For beams and frames, also write equilibrium equations for moment at the nodes. If the frame undergoes lateral displacements as a whole, the shear forces at the columns must be related to the moments at the ends of the columns. Substitute the slope deflection equations into the equilibrium equations and clear the unknown rotations and displacements at the nodes. Then substitute those results into the deflection-dependent equations to determine the internal moments at the ends of each member. If any of the results are negative, that means a counterclockwise rotation. Positive moments and displacements apply clockwise. Diagrams. Finally, By means of the data for the moments, the reactions at the ends of the beam spans, the shear force, and bending moment diagrams are made. Some illustrative examples are shown below. Thanks for watching.